So good afternoon, everyone, and this is lecture number 11. We are dealing with force on a current carrying wire, and that was the discussion that we were having in the last class. We had seen some problems in the last class, and we had seen some problem in the last class on magnetic force on a wire. And just to remind you of problem, I'll start with this problem just to give you a hint of what we were doing in the last class, magnetic force on a wire. This is a problem that you probably would have seen in your SCV as well. So simple, straightforward problem, and it comes on your screen now. A wire carrying a current I is kept in the XY plane. Y is equal to A sine 2 pi by lambda x is in the form of a sine curve. A magnetic field B exists in the z direction. Find the magnitude of magnetic force acting on the wire between x is equal to 0 to x is equal to lambda. This is a question taken from your SCV. I don't remember the question number, but it is definitely from that book. And well, you have time to solve it. I'll give you a minute to go through this. Let me know once you are done. No one with an answer up till now? To help you solve this problem, I'll give you the diagram. It might help you in solving it. So this is the diagram of the wire, and this is the current in the wire. Now, can you give me the answer? What is the force acting on this wire, which is shaped in the form of a sine wave? You have 2 minutes more. Option A. Option A is the correct answer. How did you get option A? You have to find the force on this wire. This is a wire which is kept in a uniform magnetic field. If I had to draw the magnetic field, it will be coming out of the plane of the board along the axis. The magnetic force on this random shape wire, this is not a random shape, this is sine wave. It will be equal to the wire if I join it like this straight. Whatever is the magnetic force on the green wire, that will be same as the magnetic force on the blue wire, because the net force acting on the entire loop will be going to be 0. The force on this wire is a straight wire, I into lambda into B, and that is the answer that we are looking at. Do we understand this? Yes or no? No, yes. You understand this?
Yes, sir.
Okay, one more. Most of the students were absent in the last class, so this one. A current carrying wire Ln is bent in the form as shown below. The wire carries a current of 10 amperes and it's placed in a magnetic field of 5 teslas, which acts perpendicular to the plane outwards. What will be the force experienced by this wire? You have 2 minutes to give me the answer. Yes, do we have an answer for this one? No one? You can find out the force on these 3 wires and add them vectorally. Or what you can do is you can straight away join the wire from one end to end like this. Whatever is the force acting on this green wire, the same will be the force acting on this red wire, which is joining straight. Do we understand this? Yes or no? The length of this straight wire, as you all can see, the length of this straight wire, this is just a hypotenuse of a triangle whose one side is 8 meters, 8 centimeters, and the other side is 6 centimeters. So the length of this side will be 6 square plus 10, 8 square ka root. That will be 10 centimeter. The force on this wire will be I into L into B, and the direction will be perpendicular to this wire. Length of this wire is 0.1 meters. Magnetic field is 5 Tesla. I is 10 ampere. You multiply it, and I think you will get the answer as 5 newtons. Do we understand this, everyone? Are you there in the class? Yes or no? Not getting any responses. Are you there in the class?
Yes, sir.
You understand this question, sir, or this is gone above our head, sir? Yes, sir.
Understood.
Okay, sir. Okay. One more question. Do it fast. This is the next question, and you are going to see more questions of this as time progresses. This is a question coming for you. What is the net force on the coil? I have an infinite wire carrying current 2 amperes. You'll have to find out the force on this loop of wire. And I'll give you 2 minutes to give me the answer. How are you supposed to do this? First of all, okay. Now remember, this wire, pink wire, these two pink wires. Now these two pink wires, they are placed in a non-uniform magnetic field because magnetic field changes. But these two wires, they will experience force. The current in this wire is like this, and the current in this wire is like this. Whatever force the upper wire experiences, the same force the lower wire will experience. Yes or no?
Yes, sir.
But they would not be in the same direction, they would be in the opposite direction. So these two wires will cancel each other out. Yes or no?
Yes, sir.
So basically, whatever is the net force on the loop, it will be because of the green wire which carries current in this direction and the blue wire which carries current in the opposite direction. These forces also will not be in the same direction. In which direction will the green wire experience force? Remember, the current in the original wire is upwards. In which direction will the green wire experience force? This is the original wire, infinite wire. This is the green wire. In which direction will the green wire experience force? Will it be attractive? Will it be repulsive?
Repulsive. Attractive.
Two wires which carry current in the same direction, they will always experience attractive force. So this wire will be experiencing attractive force in this direction. Let me call this as F1. What will be the value of this F1? Mu naught by 2 pi into current in the first wire, 2 ampere, multiplied by the current in the second wire, 1 mu naught I by 2 pi r. Distance is 2 into 10 raised to the power of minus 2 mu naught I by 2r. That becomes the magnetic field multiplied by the current in the second wire. That becomes the force on the first wire multiplied by the length. I forgot the length. multiplied by the length of the server I into L into B, 15 into 10 raised to the power minus 2. This 15 into 10 raised to the power minus 2 is the length of the wire. This mu naught into I by 2 pi is the magnetic field, and this one is the current. Do we understand this, everyone?
Yes, sir.
If I multiply these three quantities, forget about the if I multiply these three quantities, I think I'm going to get 3 into 10 raised to the power of minus 6 newtons. Similarly, if I want to find out the value of F2, this is F2, this F2 would be repulsive. If I want to find out the value of this F2, mu naught by 2 pi into R, 2 centimeter plus 10 centimeter, the distance is 12 centimeter. 12 into 10 to the power minus 7 multiplied by 2 ampere is the current in the first wire, which creates the field, multiplied by 1 ampere, which is the current in the second wire, multiplied by 15 into 10 raised to the power of minus 2. This is the force, and I think this force that you are going to get is 0.5 into 10 raised to the power of minus 6 newtons. Yes or no? This fuse force is repulsive, the other force is attractive, so the net force becomes 3 minus 0.5, that is 2.5 into 10 raised to the power minus 6. That is 25 into 10 raised to the power minus 6. Will it be going away from the wire or will it be towards the wire? It will be attractive because this force F1 is more compared to F2. Therefore, the correct answer is option A, 25 into 10 raised to the power of minus 7 Newton towards the wire. Do we understand this? Yes or no? No or yes?
Yes, sir.
Anyone got the answer?
No, sir.
What was the problem? Why did not you get the answer? Okay, I'll give you a minute. Note it down. Let me know. Then I will move ahead. Well, then we move ahead and we write the next heading. And the next heading is this: magnetic moment. Or if I write magnetic dipole moment of a coil. Now, as soon as I use this term, magnetic dipole moment, does it ring any bell? Do you remember anything? As soon as you hear the term magnetic dipole moment, do you hear does anything sound? Huh? No, sir. Nothing sounds. Do you remember anything? As soon as I use the word magnetic dipole moment. No one? Huh? No one remembers anything. No one remembers anything. Magnetic dipole moment. Shameful act. Do you remember anything as soon as you heard the term magnetic dipole moment? Yes or no? So, once upon a time, there was a magnet which has magnetic pole strength minus M plus M. The positive pole was known as the north pole. The negative pole was known as the south pole. And we have something known as the magnetic length, the distance between the north and the south pole. And then we defined a vector, m vector, capital M vector, which was m into L, magnetic length. This was a vector which was directed from the south pole towards the north pole of the magnet. That, my dear friend, was known as the magnetic dipole moment of a bar magnet. And some times ago, we actually studied this. When we studied this, we also took the reference of something known as this. Something known as this. This was the minus Q charge. This was the plus Q charge separated by a distance of d. This arrangement is known as an electric dipole. And this electric dipole, my dear friend, had something known as the electric dipole moment P vector. And that was given by Q into D vector. And this electric dipole moment was also directed from the negative charge towards the positive charge. It was some days back we had done this. Electric dipole moment and magnetic dipole moment. A magnetic dipole, which is nothing but a bar magnet, it creates a magnetic field. And we had found out the magnetic field due to this bar magnet at endpoints, equatorial points, and all those things. We did the similar thing for your electric dipole as well. Now, in this chapter, what we have understood is whatever a bar magnet does, a current carrying wire, or more specifically, a current carrying coil, can also do the same thing. A current carrying coil produces magnetic field. A magnetic bar magnet also produces magnetic field. So a bar magnet is always characterized by the magnetic dipole moment. Similarly, now we will take that analogy, and wherever you have electric, so wherever you have a current carrying loop or a current carrying coil, we can now take it as a magnetic dipole which has a magnetic dipole moment. A current carrying coil can be understood as a magnet, can be thought of as a magnet. This is how the magnet looks like. If the current in the coil, as you can see, is going like this, ding, 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 it's going in this direction. If it is going in this direction, it is going to create magnetic field, which is similar to a magnetic field created by a magnet, bar magnet, which is kept like this. So wherever you have a current carrying coil and you turn your fingers in the direction of current, the direction of thumb gives you the direction of magnetic field. If you consider this coil as a bar magnet, this thumb will give you the direction of north pole of the magnet. Where the north pole of the magnet is, if you understand it as a north pole. This current carrying loop can also be considered as a bar magnet. North and south, as you can see, are written there. I can define a magnetic dipole moment M vector for this. And the magnetic dipole moment M vector for this is given by this legendary I into A vector, where A vector is the area vector of this bar magnet. You must remember and recollect that area in physics is sometimes treated as a vector quantity which has a direction. Here the direction of area vector is given by the right hand thumb rule. You turn your fingers in the direction of current. The direction of thumb gives you the direction of area vector, which is the direction of north pole, which is the direction of magnetic field, which is the direction of magnetic dipole moment. So every current carrying coil now becomes a magnetic dipole. It becomes like a magnet and it now has a magnetic dipole moment. I hope you have understood the significance of this. Just to make you understand it further, you can see this diagram at the end. If the coil carries current in this direction, it could be a rectangular coil, it could be a square, it could be a ring shaped coil. You turn your fingers, the direction of thumb also gives you the direction of north pole. It also gives you the direction of the magnetic dipole moment. I'll give you 2 minutes to note it down.
Done, sir.
Okay, then let's move ahead, sir. If you can find out the direction of magnetic dipole moment by turning your fingers, or you can, if the current carrying coil lies in your loop, in your plane, where the north pole is and where the south pole is, you can, instead of turning your fingers, if the current is anti-clockwise, the north pole will be pointed towards you. You can see, you can write north pole ka N in this fashion. So if you see an anti-clockwise current in a coil, that means the north pole of the magnet is pointing towards you. If you see clockwise current in a coil, the south pole is pointing towards you. So clockwise current means south pole, anti-clockwise current means north pole. Do we understand this north-south analogy? So this is one other way in which you can understand the same thing. And wherever there is north pole, the magnetic dipole moment is coming from south to north, so it is directed from south towards north. If the coil has one loop, then the magnetic dipole moment m vector would be given by I into a vector, where a is the direction of the area vector. I have told you that if there are n turns, if there are n turns, then the magnetic dipole moment will become n times IA. I hope you understand this. Everyone, can't see you, I don't have a mic to talk, but I hope you understand what I am saying. Yes or no? No or yes? If you want, you can also write the direction of magnetic dipole moment. I have told you so many ways of finding out the direction. You can also find out the direction by the right hand thumb rule. Turn your fingers in the direction of current. The direction of thumb will give you the direction of magnetic dipole moment. I'll give you 1 minute to note this down. Let me know once you are done. Let's move ahead and let me present to you this question. A loop A, B, C, D, E, F, A is in the form of this loop. The current in the loop is 2 amperes. You have to find out the magnetic moment of this loop. I'll give you 2 minutes to give me the answer. Now is the time that I am going to solve this for you. It basically consists of two square loops. I hope you understand this. Yes or no? Huh? Yes or no?
Sir.
What, sir? Everyone is there in the class, no, sir, or everyone is chilling out?
Yes, sir.
Chilling out, sir?
No, sir.
Looks like everyone is chilling out. So this is the enlarged view of the same thing so that you can understand it. I can break this up Basically, this consists of two loops. The pink loop, pink loop is like this. You can find the magnetic moment of that loop, and the magnetic moment of this loop will be going along the y-axis. Yes or no? Huh? Yes or no? Huh? You understand this? Or bye bye. Then you have this blue loop which is in the xy plane. Yes or no?
Sir.
And the magnetic moment of this loop is going to come outside. Oh, sorry, inside. Yes or no?
Yes, sir.
I have marked this one also wrongly. This is not coming up. This is coming down actually. Take the, if I just turn the fingers, for the XY loop, it is going inside. For the XY loop, it is going inside. And for this group, this loop, it is going down. Yes or no? Both the magnetic moments are equal in magnitude. This is also M, which is equal to I multiplied by A. Yes or no? And this is also equal to M, which is I multiplied by A. Yes or no? One is going along negative J axis, negative Y axis. The other one is going along negative Z axis. The net dipole moment will be root over m square plus m square. Yes or no? So it will be root over 2 times m. Do we understand this? Huh?
Yes, sir.
What, sir? And this m is nothing but I. I is 2 ampere multiplied by 10 into the power 10 into 10 raised to the power of minus 2. And that is your answer. And that has to be multiplied by root 2. The answer that I have is 0.028. 0.028 ampere meter square. Is that what you are getting? Anyone? Huh? No one is getting that. Anyone getting this answer? Yes or no? Or everyone chilling out? Are?
No, sir.
Chilling out, no?
No, sir.
It's good time to chill out.
Sir.
No, na?
No.
Then you have this question coming for you, sir. The while loop PQRSP, PQRSP is formed by joining two semicircular wire of radii R1 and R2, carries a current I as shown in the figure. What is the magnetic induction at point O and the magnetic moment of the loop in cases A and case B? You have 2 minutes to give me the answer for this one. Let us first solve it for the case A. For the case A, the current in the wire is like this, as you can see. The magnetic field due to the pink wire will be coming out, and magnetic field due to the green wire will be going in. Yes or no? And the magnetic field due to pink wire, since the radius is small, will be more. So the net magnetic field, B net, will be mu naught into I by 4 pi into pi, 1 by R1 minus 1 by R2 and the direction will be going outwards. Do we understand this? Yes or no? No or yes? Do we understand this? That is the net magnetic field. If I want to find the net dipole moment, current is I. The radius of the first one is pi r1 square. The radius of the second one is pi r2 square. Because of the outer one, the magnetic moment is inside. Due to the inner one, the magnetic moment is outside. But here, outer moment is more, inner moment is less. Radius is pi r square by 2. So the answer is pi I by 2 r2 square minus r1 square, and the direction is cross. Everyone understands this? Yes or no? What I have done here?
Yes, sir.
If I move on to the section 2, magnetic field due to the blue wire or pink wire and green wire and magnetic moment due to all of this, everything is getting added up. Yes or no? Magnetic moment is also going in the inward direction and magnetic field is also going in the inward direction. So for case B, we have the net magnetic field as mu naught I by 4 into 1 by R1 plus 1 by R2. Everything is going inside. The net dipole moment mu naught, oh sorry, not mu naught, pi I by 2 R1 square plus R2 square, both going inside. Do we understand this? Yes or no? No, yes. You have 2 minutes to note down the answer. Here comes a question which is from your recent exams 2018 JEE Main. The dipole moment of a circular loop carrying a current I is M, and the magnetic field at the center of the loop is B1. When the dipole moment is doubled by keeping the current constant, the magnetic field at the center of the loop is B2. These are the type of questions that you get in the examination hall, which are very simple if you understand the concept and you can do them very quickly. What is the ratio of B1 by B2? Your time starts now. So, how are we supposed to do this? The initial magnetic dipole moment, the magnetic dipole moment of any magnet, of any current carrying coil is I into A. Initially, the magnetic dipole moment is M. So let me write this M is equal to I into pi r squared. The magnetic dipole moment is doubled by keeping the current constant. So the new magnetic dipole moment becomes 2m and current has to be same. So the radius should become root 2 times of r. So radius becomes root 2 times of r. In first case, the magnetic field is mu naught I by 2r. It is inversely proportional to r. In the next case, b dash will become mu naught I by 2 times root 2r. Magnetic field B1 by B2. B1 is the original field, B2 is the new field, and the answer has to be option D. And this is the answer that we are looking at. Anyone got this answer? Well, I'll give you 2 minutes to note this down. Welcome. The next question, sir. This is from IIT-JEE Advanced of 2012. Not means, this is JEE advanced. The question is right there in front of you. You have a loop carrying some current, and you have to find the magnetic dipole moment of the loop. You have 2 minutes to give me the answer for this one. Well, in this, you just need to find out the area of this entire thing. So you can think it of as a square. The pink one is a square. And if you look at the green ones, the green one, if you add all the green ones together, you will get 2 circles, 2 full circles. If you add all the green ones together, you will get 2 full circles. You just have to find out the area. You know the direction of current. The direction of current is like this. So it is coming along K. The area of the pink part is A square. The area of the green part is 2 times the area of a circle, which is pi d square by 4. D is A, so it is pi d square by 4 plus pi d square by 4, and the direction is K. The only option which matches all this is option B, and that is the correct option. I will give you 2 minutes to note this down. That takes us to the next thing, coil or current carrying coil or magnetic dipole. Or electric dipole in an electric field. This is magnetic dipole in a magnetic field. I have already told you everything that you needed to know about this magnetic dipole in a magnetic field. What happens to the magnetic dipole in a magnetic field? What happens to a magnetic dipole in the magnetic field? Does anyone remember? If a magnetic dipole is placed in a magnetic field, your magnetic field is going in this direction. Your magnetic dipole moment is in this direction. Anyone remembers this? Anyone recollects this? And the angle between the two. The angle between the two. The angle between the two is theta. This magnetic magnetic dipole, the force acting on this dipole is 0, and the torque acting on this dipole is given by m cross b. Do we remember this? If
Yes,
I
sir.
write it in the scalar form,
MB sin theta.
mb sine theta. If theta is 0, torque is 0,
Equilibrium.
theta is 0, torque is 0. This equilibrium was known as the stable equilibrium. If theta is 180, torque is again 0, but this equilibrium is known as unstable equilibrium. If theta is 90, then torque is maximum. Yes or no? No or yes?
Yes, sir.
If theta is 90, torque is maximum, tau max is equal to mb sine theta. That was the case for your bar magnet. The same case could be written for your current carrying coil. Do we understand this? So this is going above our head saying bye bye, bye bye, bye bye. I'm going bye bye. Huh? Force is 0. Tau is m cross b. The only thing is here m is I into a vector. The rest of the things remain same. Do we understand this? Or this is going above our head saying bye bye, bye bye, bye bye. Going bye bye, bye bye, bye bye. Huh?
Understood, sir.
Same thing here. This gentleman. Oi, 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 oi. Oi, 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 oi. Minus Q, plus Q. And then we have this revolutionary magnetic field. B in this direction. Dung, 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 dung. The force acting on this electric dipole is 0. The torque acting on this electric dipole is P cross E. Why have written B? It should be E. Do we understand this, or this is going above our head saying bye bye, bye bye, bye bye, and bye bye, bye bye? Electric field E vector. Force is 0. Tau is P cross E. Rest is same. You have 2 minutes to show your talents. Well, then you can note down these important points. Just as a reminder, torque on a dipole is an axial vector. Torque is an axial vector. It is directed along the axis of the rotation of the dipole. So dipole is going to rotate along that axis in which the torque is there. Normally an axis passing through the center of mass of that. Now this tendency of this torque is to bring the dipole back to its position of stable equilibrium. Do we understand this? It will try to align M in the direction of B, or it will try to bring what? The dipole back to its stable equilibrium position where theta is equal to 0. Do we understand this, or this is going above our saying bye bye? Bye bye, bye bye, bye bye. Bye bye.
Understanding, sir.
If a dipole is placed in a uniform magnetic field, force is 0, torque may be 0, it may not be 0. Do we understand this?
Yes, sir.
If the dipole is in a non-uniform magnetic field, force is definitely not 0. Torque may or may not be 0, depending on the value of the angle theta between M and B or P and D or whatever. Do we understand this? If the current carrying coil is placed in a longitudinal field, when I say longitudinal field, along the plane in which the loop is, because the magnetic moment of the loop is perpendicular to the loop. Do we understand this? So basically they are saying if the angle between the area vector and magnetic field is 90, torque is maximum. If the angle between area vector and magnetic field is 0, torque is 0. We understand this? Yes or no? No, yes.
Yes, sir.
2 minutes to note it down. So we
And
move
sir,
ahead, and what is the next thing that comes? The next thing that comes is the potential energy of a dipole. PE, potential energy of a dipole in a magnetic field or an electric field. And without saying much about this, the potential energy of a dipole in a magnetic field or electric field is given by minus M dot B,
cos theta.
or it is minus P dot E. Do we understand this? Yes or no? No, yes. In terms of the dot product, we can write it M dot B. In terms of scalar, I can write it as minus MB cos theta or minus PE cos theta. Do we understand this? Yes or no? No, yes. If theta is 0, U is minimum, which is equal to minus MB, and this equation is known as the stable equilibrium, whether it is for magnetic dipole or electric dipole. Do we understand this? If theta is 180, it is U max, that is plus MB. This is the unstable. Everyone understands this? Yes or no? No or yes?
Yes, sir.
So the same thing written in terms of word. Potential energy minimum, stable equilibrium, potential energy maximum, unstable equilibrium, whether it is electric dipole or it is magnetic dipole. Everyone understands this? Yes or no? No or yes? Huh? You have 2 minutes to show your talents. That takes us to the next heading, work done in rotating a dipole. What is the work done in rotating a dipole? And we have discussed it so many times. Work done in rotating it from theta 1 to theta 2 by magnetic force, MF, magnetic force. It will be energy at theta 1 minus energy at theta 2. Do we remember this? Work done in rotating it from theta 1 to theta 2 by electrostatic force. Let me not write electrostatic force. I hope you can understand this because it will just create confusion. Magnetic force, magnetic field. So if I just elaborate this, it will become minus MB into cos of theta 1 minus cos of theta 2. Do we understand this? Yes or no?
Yes, sir.
On the other hand, if sometimes they ask us work done in rotating from theta 1 to theta 2 by external force, that will be equal to U at theta 2 final energy minus initial energy, provided that change in kinetic energy is 0. So remember the difference between the two. So this will become minus MB into cos of theta 1, sorry, cos of theta 2 minus cos of theta 1. Do we understand this?
You have written theta 2.
I have written it wrongly. This would be theta 2 minus theta 1. Okay? I'll give you 2 minutes to note it down. Then this is a small question, sir. You have a uniform magnetic field of 5,000 Gauss established along the positive z-axis. Remember the axes are somewhat different from your normal things. A rectangular loop of size 20 centimeters and 5 centimeters carries a current 10 ampere is suspended in this magnetic field. What is the torque on the loop in the different cases in the following figures? What is the force in each case? Which case corresponds to stable equilibrium? I think you can give the answer for the second question. What is the force in each case on the loop? Yes, my dear friends. You can give me the answer for this one to start off the question. What is the force in each case on all the loops? A, B, C, D, E, F, G, and the answer is? Huh? No one knows the answer? Shameful act? No one knows the answer? What is the force in each case? Huh? Anyone knows the answer to this part? Anyone knows the answer for this part? The force in each case is 0. So I'll give you the rest of the question and I'll wait. Okay, let us go ahead and solve. In all the 6 cases, it is a current carrying loop is placed in a uniform magnetic field. So in all these cases, the force acting on the loop is 0. Do we understand this? Yes or no? I'm not getting any voices. Do we understand this?
Sir.
F is equal to 0. Okay. Now, in all the cases, you can find out the magnetic moment of the loop. Yes or no? It is NIA. N is 1 here. I is given, area is given. You just have to find out the direction. In this case, the direction is coming out of the magnetic dipole moment. Yes or no? Yes or no? Here, also the direction of magnetic dipole moment is outside. This loop is kept in the ZX plane, loop number 3. If I turn my finger, the direction of magnetic dipole moment is in this direction. Fourth case is a bit different, so we'll do it. Let's first do the other case. In case number 5, the magnetic dipole moment is M. In case number 6, the magnetic dipole moment is M downwards. Do we all understand this? Yes or no?
Yes, sir.
In case number 1, the angle between magnetic dipole moment and magnetic field is 90. Yes or no? So the torque will be M into B into sine of 90, M into B. Do we understand this? Yes or no?
Yes, sir.
In the second case also, the angle between M and B is 90. So torque is M into B. Yes or no?
Yes, sir.
In the third case also, the angle between M and B is 90. The torque is M into B into sine 90, M into B. Yes or no?
Yes, sir.
In the fifth case, M and B are in the same direction. So torque is 0. This is the case of stable equilibrium. Do we understand this? Yes or no?
Yes, sir.
Here, again the torque is 0. But this is the case of angle between M and B is 180. This is the case of unstable equilibrium. Do we understand this?
Yes, sir.
The only case that remained is case number 5. Where is the magnetic dipole moment directed? The value of magnetic dipole moment is M into B. You just have to find out the angle between M and B. Now, how are you going to find out the angle? See, magnetic field is along y-axis. This loop is in the xz plane. If this loop, if you look at this case number 3, this loop was along the zx axis. So the angle between magnetic field and this loop was 90 degrees. Do we understand this? But now this loop has been turned. See, the loop ka magnetic dipole moment was like this. Now it has turned by 60 degrees. So it goes like this, 60 degrees. Yes or no?
Sir.
So the angle between magnetic field here, you can see magnetic field is going like this, B. Yes or no? Now, when this loop was along this axis, the magnetic dipole moment was going along y-axis. But now it has turned 60 degrees. So the magnetic dipole moment will be going 60 degrees this side. Yes or no? Do we understand what I said?
Yes, sir.
When the loop was like this, magnetic dipole moment was along y-axis. The loop has turned by 60 degrees. This is the 60 degrees the loop has turned. So from y-axis, it will turn by 60 degrees. Do we understand this? So the angle becomes, do we understand this? Okay, leave this question here. Do we understand the rest of the 5?
Yes, sir.
You understand the rest of the 5?
Sir.
We'll do this question afterwards. We understand the rest of the 5?
Yes, sir.
I will go ahead and do the next question one, and we will discuss this question in the coming class. Okay, forget about this one. Okay, we'll do this in the next class. I have to do one more question before I end this class, otherwise my thing will remain half. So this is the last question. You do it first, and then we will discuss this question in the next class. This is the question that I want you to do in place of that question. This one, a circular coil of 100 turns and having a radius 0.05 meters carries a current of 0.1 ampere. Calculate the work required to turn the coil in an external field of 1.5 Tesla through 180 degrees about an axis perpendicular to the magnetic field. The coil is initially at right angles to the field. Coil is initially right angles to the field. And I have to turn it by 180 degrees. I'll give you 2 minutes to think about this. So how are we going to do this? It will be easier if you can draw the diagram. Now, plane of the coil is initially at right angles to the magnetic field. So if I draw the magnetic field like this, the plane of the coil is initially at right angles. That means the area vector of the coil will be along the same direction. Do we understand this? Area vector means the magnetic dipole moment will be in the same direction. I have to turn from this direction and I have to take it to this direction where it has 180 degrees. Do we understand this? This is the coil. This is the magnetic field. The area of the coil is perpendicular to the magnetic field. Do we understand this?
Yes, sir.
Therefore, the area vector and the magnetic dipole moment, they are in the same direction, which is the direction of magnetic field. So I have to turn it from this position, position number 1, to this position, position number 2. This is the work done by external force. It is not mentioned because it will not move on its own. So this is the work done by the external force in moving it from 0 to 180 degrees. Do we understand this? By the external force. So this will be equal to energy at 180 degrees minus energy at 0 degrees. Do we understand this?
Sir.
Yes or no? Energy at 100. So I take minus MB outside. Cos of 180 minus cos of 0. Do we understand this? So cos of 180 is minus 1, cos of 0 is plus 1, minus 1, minus 1, minus 2, minus 2 into minus. Answer will be 2 times of MB. That would be the answer that we are looking at. Do we get this? Yes or no?
Yes, sir.
Well, that was a question that I had to done to rotate. How to find out the work done in rotation. That's all from this class. I'll see you tomorrow and we'll try to wind up whatever things are remaining and try to solve some more problems. Okay. I hope you have understood what we have done in today's class. Yes or no?
Yes, sir.
We'll join today and we'll wind up the thing by tomorrow. Take care. God bless you all. Bye bye.
Bye, sir.